Hello everyone, welcome to join us. Today's class is going to introduce Keras, one of the most popular deep learning framework in the world, and has become the front end of TensorFlow 2. I will talk about the origin of Keras, deep learning basics, and how to build neural networks with Keras. I will also show you how to use Keras to solve real-world problems such as movie review classification or housing price prediction. After today, you will be able to develop your own neural networks. What is Keras? Keras is a high-level neural networks API written in Python and capable of running on top of TensorFlow, CNTK, and Fiano. In other words, Keras is not a standalone deep learning framework. It needs to running on top of TensorFlow, Fiano, or CNTK. Fiano and CNTK are out of line today, so it's running on top of TensorFlow. And the deep learning frameworks need to communicate with the hardware resource like GPU or CPU through the libraries such as CUDA, developed by NVIDIA, and plus Eigen, open source library. So the deep learning framework can calculate the gradient and do gradient descent for us. Also accelerating the process by using the library CUDA or BLAS. Keras was developed by Francois Cholle. Mr. Cholle is a Google engineer. Keras was his personal project. He wants to simplify the complicated interface of TensorFlow and used Keras to accelerate his research project. This project was so successful that more and more researchers choose to use Keras instead of TensorFlow. So eventually, Keras was officially supported by TensorFlow 2.0. So after TensorFlow 2.0, you will use Keras as your interface. In this class, we use the book written by Francois Cholle, Deep Learning with Python. However, the book was published in 2017, and the examples are based on TensorFlow 1. Now all the Colab and the Cargo are migrate to the TensorFlow 2. So if you want to run the examples in our slides on TensorFlow 2, there are several tricks. The first one is to import the TensorFlow Compact v1 STF and disable the version 2 behavior. The second one is to run in the Keras code using the change the package Keras to TensorFlow.keras. And last one is to run the code on Colab. You just need to add the magic TensorFlow version 1.x magic. Therefore, by adding a few lines, you can run all the examples in this slide on TensorFlow 2 framework. Before we start writing code, let's look at some terminologies of a neural network. First, a neural network consists of multiple layers. So the first terminology is layer. And then each layer contains many parameters, which will be updated by our training algorithm. In machine learning, we call the parameters weights. So we have multiple layers, and each layer has many weights. Then we feed the input x into our model. Then after going through multiple layer data transformation, we will have predictions. The prediction y prime will be compared with the true target and calculate the difference using the loss function. So we need to define the loss function. And finally, we will get a loss score. Our goal is to minimize the loss score using the optimizer. The optimizer will update the weights. or we call it training or learning. We train the weights to make the prediction y prime, which are as close as to the true targets. In other words, we try to update our weights to minimize the loss score. Now we are ready to build our own networks with Keras. Keras API are so easy to use. They will make you like playing Legos. You just need to define each function of each layer and then stack them together. Let's start with handwritten digits classification, which is the hello world of deep learning. The task is to classify grayscale images of handwritten digits, which are 28 by 28 pixels, into their 10 categories, from 0 to 9. So we have 10 classes, and each input sample is a grayscale image, which has 28 by 28 pixels. The MNIST dataset was created by Yanmakan, which has 60,000 training data and 10,000 test images. Here are some examples from the MNIST dataset. You can see the 0, 2, 4, and 3. You can find the code here on the collab. The first step is to download the MNIST dataset using Keras API. We can see how friendly Keras is here. It even prepared and uploaded the dataset for us. So we first from the keras.dataset and import the MNIST dataset and call the load data function of MNIST. It will download the object from the cloud server and return 4 objects: train images, train labels, test images, and test labels. So we are going to solve a supervised learning problem. Here's an important thing to note, that we need to split the dataset into train images and test images. And the most important of all, never use the test image for training. Otherwise, you will overfit your model. Okay, now let's run the MNIST code on Colab. First, we import the MNIST data, and Keras shows that using TensorFlow backend. And then we load data. The message shows that it downloads data from the Amazon cloud service. MNIST NPZ. That's the NumPy zip file format. And then we show the tensor, the axis of our training data, training images. We can use shape to print the number of data along each axis. So we can see that we have 60,000 images, and each one has 28 times 28 pixels. Right. So we can use shape to see the number of data along each dimension, along each axis. If we just want to know how many data we have, we can use length. And then it returns 60,000. For the train labels, we can print it. We just type the name of labels and it will print labels. So labels is an array, right? It contains the answer of each image, which number of the image it has. So the first one is 5, the second one is 0, the third is 4. In terms of test images, we can also print the shape of test images, and it's 10,000 28 by 28. So as we can see, all the data are prepared as tensor and ready to pass into our neural networks. Okay, so again, we can print the test tables to see what's the answer of our test data. Let's take a detailed look at digital images. And digital image is just an array of numbers. Specifically, an array of unsigned integer with 8 bits. For each integer, we can use a byte, 8 bits, to represent a pixel. This value means how bright that pixel is. So 0 means no color at all, which means black. So we can visualize this array, and it shows a number 5 at the left side. The black parts are the zeros in the array, right? And then the white part is very close to the maximum value of the 8-bit, which is 255. The range of an unsigned integer 8-bit is from 0 to 255. So you can understand what are the digital images. For grayscale images, it's just a 2D array. For colorful images, it will be a 3D array, which include width and height and also RGB pixels. We also call them channels of and colorful digital image. So how can we see the images? We can use the matplotlib matrix plot library to visualize the array. So we just import a pie plot in the matplotlib. We give it a nickname plt, and then we call the image show imshow function and pass the first image in our tensor to the plt. And we can assign a color map because it's a grayscale, so we assign gray. The result is here. Note that we need to add this metric matplotlib inline to show the images, but it's not necessary on collab now. Now we are ready to build our first deep learning model. Let's build a model shown in 3 brown 1 blue's video. He shown this example to classify MNIST dataset. So the first is actually not a neural network layer, it's an input vector, which is 784 pixels in a 28 by 28 grayscale image. So the model has 2 hidden layers, each with 16 neurons, and the output layer has 10 neurons, which corresponding to the 10 class from 0 to 9 in a MNIST dataset. To build a neural network using Keras, we first import models and layers. A model can contain multiple types of layers. Here we use 2 types of layers. The first one is dense layer, which means fully connected neural layer. The input is fully connected to the output of previous layer. The second is softmax layer, which outputs the probabilities of all the class, which is 10 in MNIST dataset, the number from 0 to 9. So here is how we build the model in 3 brown 1 blue's video. First, we create a sequential models. A sequential model means there is no branch of our neural networks. We will see more advanced model in the future class. Then we add the first dense layer in the network. For the first layer, we need to assign the dimension of the input data, which is 28 by 28 grayscale images. You may notice that we omit the number of samples because we want to let the user decide how many samples they want to put into our model each time, which are called bench size. The activation function is ReLU, which is the most popular activation function. The second hidden layer is also a layer with 16. Dense layer with 16 neurons. And we can omit the input size now because Keras will automatically use the output of previous layer as the input. so we don't need to assign the input shape here. But then we add the final output layer, which is a layer with 10 neurons, and we use softmax as activation function. Softmax is the go-to activation function for multi-class classification. After creating our model, now we are ready to compile it. During compilation, Keras will check the connection of our different layers. And also we need to define 3 important parameters. Okay, the first one is the loss function. The loss function is used to measure the performance on training data. Okay, and in the MNIST dataset, we use the categorical cross entropy. We will see that we will always use categorical cross entropy for multi-class classification. The second parameter that we need to design is the optimizer. Okay, there are many different types of optimizer. They are all based on gradient descent. So we can choose the one we like. We can try different optimizer to see if the performance is better or not. The last one is the matrix. So the matrix is used to evaluate the performance on test data. Here we use accuracy because the MNIST dataset is very balanced. Once we compiled our model, we can call the function summary to print the summary of our model. So let's call the summary of our model network. Okay, the model is named the sequential 1. Keras named the model and the layers automatically. We have 3 layers, dense 1, dense 2, and dense 3. Okay, and here's the output shape. The output shape for the 2 hidden layers are all 16, and for the final output layer is 10. Also, it will show how many parameters are there in a layer, right? Remember how to calculate the parameters. Let's use the second layer as an example. So for the second layer, the parameters will be the input 16 times the neurons in this layer, both are 16, plus the bias. Okay, each neuron in dense 2 layer has a bias. Okay, bias parameter, right? It's used as a threshold for the activation function. So totally we have 272 weights. Alright, so you can do the calculation for other layers by yourself. So the total number of parameters are 13,000, right? 13,000. So that's a lot of parameters for such a small network. Now our model is ready. So we need to prepare the data and the labels. For the data, we want to do normalization. In other words, we want to remap the training data from 0 to 255 to 0 and 1, or between 0 and 1. That will make the training process more easier. Okay. It will make the optimizer easier to optimize the model. So first we convert the data into the floating point, the 32-bit. So that we can have a floating point, and then divide all the pixels with 255, which is the maximum value of a pixel. So once all the pixels are divided by 251, all the new pixel values are between 0 and 1. So we need to both normalize the training and the testing data. Also, we reshape the data. We reshape the image data, the image into the 28 by 28, 28 times 28 one-dimensional vector. It's not necessary. Depends on your choice, because Keras can accept 3D tensors. So in this case, after reshaping, the 3D tensor becomes a 2D tensors. Okay, after we prepare the data, we now need to process the labels. Remember that our output are a 10-dimensional vector, right? So we need to convert the data labels. The original data labels are numbers. We need to convert the numbers into 10-dimensional vector. We use the method called one-hot encoding. One-hot. In Keras, we can just call the two categorical to convert integer labels into one-hot encoded vectors. Let me show you a figure of one-hot encoding so you can have better understanding. Okay, suppose we have four classes, 0, 1, 2, and 3. So our output layer, the softmax, will be a 4-dimensional vector, right? So for the first class 0, we will use the first entry in the 4-dimensional vector to represent the class 0, right? And we use the second entry to represent class 1, and the third for class 2, and the fourth for class 3. So as you can see, in a 4-dimensional vector, there is only one entry is equals 1. Others are equal to 0. So this is why the conversion called one-hot encoding. You always have only one class equals 1 and the others equals 0. After compilation, we can train our model now. Okay, we call the function fit to train our model. Fit is the terminology used in statistics. So we pass the training images as well as the training labels. And there are two more parameters we need to assign. The first is epochs. Epoch is how many times your model have seen all the training samples in the data set. The second one is bench size. This is how many samples each time your model used for training. So we have a bench size because usually we cannot put all the training data into the memory of our GPU. If you are rich and has a GPU with big memory, then you can use larger batch size. It may converge faster, or you can use smaller bench size. Okay, so after we run the fit function, it will print those messages. First, it will start from epoch 1. We assign 5 epochs. So it will show the progress of using running through all the samples in the dataset, which is 60,000, right? And we will show the loss score as well as the metrics. We use accuracy. So at the first time, our accuracy is 0.92, which is not bad. After 5 rounds, after 5 epochs, you can see that the accuracy is as high as 98.89, which is pretty good. Note that you will have different results each time. Every time you run this training process, it's very normal for deep learning. Here is the complete code of training a model to classify handwritten digits in MNIST dataset. But here the model is a little bit different. In previous model, we have 3 layers, 2 hidden layers with 16 neurons. And here is the model from Chole's textbook, Deep Learning with Python. So he used only 1 hidden layer with 512 neurons. You can try different models, different layers, different number of neurons to see which model has better performance. And then we compile the model. Other parts are the same. We compile the model and we do data pre-processing. We do normalization to convert the pixel as floating point and the range, limited range between 0 and 1. And then we encode our labels as one-hot encoding. as one hard vector. Finally, we train the model using the fit function and assign the epochs to 5 and select batch size as 128. After training process is done, we need to evaluate our model on test dataset. Remember, only generalization net count, which means only the accuracy on the test set is real accuracy of your model. Okay, so let's call the evaluation function of Keras model and pass the test images as well as the test labels. Okay, so here's the result. It will print these messages. So there are 10,000 test images in the dataset, and the final accuracy is 0.9776, which is slightly worse than the accuracy on training dataset. This is normal. If you get higher accuracy on test set, you should dump your model. Okay, you should recheck your model. It is possible because the test accuracy depends on your test dataset. However, if you got higher accuracy than the accuracy on training dataset, you should recheck because it seldom happened. The evaluate function will go through all the data in the test dataset. So what if we just want to classify a single image? Here is the solution. We can call the predict function of Keras model. Okay, so let's call the predict and pass only one image. The first image, or pass only one sample, and it will return the probabilities. It actually returns the output of the final softmax layer. So this is the probability of test image 1 as each of the 10 class. So we need to find the one with maximum probability. We can use the argument max. Argument max will find the max number in an array and return the index. Okay, so let's use the argument max function of NumPy, and it returns 7. Okay, so let's see the answer. The answer in the test labels is also 7, so our prediction is correct. Okay, we have learned the first example, MNIST, which is a multi-class classification problem. But as we know, there are many different types of machine learning problems. For example, classification, regression, clustering, or dimensionality reduction. So in the rest of the class, we will see more types of problems, such as regression and binary classification. We will focus only on the supervised learning in today's class. For other types of problems, we will introduce in other class. How to build model for different problems, such as classification and regression. Actually, in deep learning, it's just about choosing the right last layer activation function and loss function. So here's a table. This table is very important. Please memorize it and understand it. So this defines the different problem type and the corresponding last layer activation and the loss function. So the first is binary classification. For binary classification, we can use logistic regression. So the last layer activation function is sigmoid, and we should use the binary cross entropy for the logistic regression. For multi-class single label classification, which like MNIST, we use softmax. We have seen this, and use the categorical cross entropy. For the multi-class multi-label classification, this means that each image can have multiple labels. For example, like hashtag, image hashtag, you may have multiple hashtags like love, dog, or beauty. or something else, then this problem becomes a multi-level problem. For the multi-class multi-level problem, the activation function become sigmoid, and the binary cross entropy is just like the binary classification, but you will have multiple sigmoid functions. Keras will handle this for you. For a regression to arbitrary values like stock price prediction or housing price prediction, we will see an example. There's no less layer activation, no activation function. And you can use the mean square error as the loss function. For regression to values between 0 and 1, actually this is logistic regression. So it's similar to the binary classification. You can use sigmoid as the last activation function and MSE or binary cross entropy for loss function. So please remember this table and understand it. For deep learning, to solve different problems usually means choosing the right less layer activation and the loss function. Let's move on to see more examples, which can help us to understand how to choose the right activation and the loss functions. There are 3 examples of real-life machine learning problems. The first one is movie review classification. The goal is to check to classify if a movie review is positive or negative. So this is a binary classification problem. We have 50,000 polarized reviews from Imdb. The second problem is Thomson Reuters financial news classification. And we need to classify 64 different topics news. So there are 64 exclusive topics, including the earn, grade, crew, trade, 46 different financial topics. But this is the same type of problem as MNIST multi-class classification, which we have learned. So it's similar, just with more topics, and we need to handle the tags. The third one is predicting housing price. So this is a regression problem because housing price is continuous. We will use the Boston housing price dataset, which has 506 samples with 13 features. This is a small dataset, but it can show us how to use deep learning to solve regression problem. Let's look at our first example, which is to check if a movie review is positive or negative. This is a binary classification problem. We use Imdb movie review dataset. It's the most famous movie dataset on the movie database on the internet. I'm sure you have used it more or less before. The full name of Imdb is Internet Movie Database. Someone has collected 50,000 polarized reviews. Polarized means either the review is very positive or very negative. And this is a balanced data set. There are 50% positive and 50% negative reviews in the data set. It was a cargo competition. You can check the link. So the goal is to check to classify if a review is positive or negative. The first step is to load the Imdb dataset. Again, Keras has prepared the dataset for us. So we just need to import the Imdb data from the keras.datasets. And again, we just call the load data function. But now we have a new parameter this time. It's called the number of words. Okay. This parameter is to select the most frequently used words in all the review texts. Okay, because there are many words or some of them are rarely used. For example, some actors' names or directors' names. So we just want to keep the most frequently used words. So or otherwise our vector dimension of a review will be too large. So we keep the 10,000 frequently used frequent words. And then we can print the train data. Okay. Now we can see the downloaded data has become a series of integers. It's not the original review. Keras has preprocessed it and converts all the words into integer index. So we receive a series of integers for each review. How can we decode the integer series back into English so we can read the article? Here is how. First, we need to get the word index. This function will download data from the Amazon or cloud service and return the word index dictionary. To convert integer back into the word, we need to reverse the key value in the word index dictionary. So we use a for loop to read all the key value pair in the word index word index dictionary. Then return the reverse version and make a new dictionary called reverse word index. Then for every integer in the training data, we select the 11th data, training data to decode back to English. So for every integer in this training sample, we call a reverse word index to get its original word. However, the index need to deduct by 3 because Keras model use 0, 1, and 2 for padding, start of sequence, and unknown. So we need to offset by 3. And for unknown word, if we cannot find the index in our dictionary, we just print question mark. Then we join, connect all the words together, separate by a space. So this is the final decoded review. Let's print the review. The review is here. So first is a question mark. It's probably a name. So it's not in our most frequent 10,000 words. The other words are French horror cinema has seen something of a revival over the last couple of years with great films. Blah 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 blah. And here, he says one of the best French horror films ever made. So we guess it's a positive review. Okay, so it's a good practice to sometimes convert your training sample back into original text. Also, you can check if you have convert your training sample correctly. After downloading the data, we need to pre-process the data. There are two things. First, we need to make all the reviews have the same length so we can compact them or stack them as a tensor. So we need to cut the review that is longer than our default length. And also we need to pad a list that's shorter than the default length, default dimension. And then we need to transform the integer data into the one-hot encoding format. So we define a function called the vectorizing sequence, the text sequence. And the default dimension is 10,000 10,000, which is the number of words, the number of words in a review. And then we need to get the number of texts, or the number of sequence, the number of reviews. So we create a tensor zero matrix with the number of reviews and the number of words in an article. So it's a sequence length by the review dimension. Okay, and then we enumerate all the word in a sequence. Then we assign. We are encode the integer data into a one-hot encoding format. So whenever we got an index, we set the corresponding entry to 1. So in fact, it's a multi-hot encoding format. In addition to the one-hot encoding we have seen before, it will have multiple 1 in the encoding vector, because whenever a word happens, then the corresponding entry will be set to 1. So this is how we vectorize a sequence, convert the article into a multi-hot encoding format. One drawback of this approach is that you lose the frequency of the words. So for example, if there are multiple best, the word best in a review, you just get one hot encode, because it happened although it's happened multiple times, we only have one entry to record it's occurring. So there's a drawback of the one-hot encoding format. Let's vectorize the train data and test data using the function defined in previous slide. And then we print out the first review in the training data. We just print the first 100 words, okay, because there are 10,000 too much to be displayed on the Colab notebook. So as you can see, there are multiple ones in this vector. So it's actually multi-hot encoding of a review. After vectorize the train and test data, remember to convert the labels into a floating point. The labels are either 1 or 0. 0 means negative and 1 means positive. Now it's time to create our neural network model. So we create a sequential model using models, and we want to create a 3-layer networks with 2 hidden layers of 16 neurons and 1 output layer. So basically you can choose whatever number you want, whatever number of neurons you want. But in this case, we need to choose small number because our input is huge, it's 10,000. So there will be a lot of parameters if we choose larger neurons. In this layer, for example, 500, and then the input parameter will be the 500 times the 10,000 plus the 500 bias, or it will be huge. You will have 5 million weights in this layer. Okay. So the key difference between this neural network and the previous MNIST network is the activation function. From the table in previous slide, we know that we need to choose sigmoid activation function for binary classification problem. And also when we compile the model, we need to choose a binary cross entropy loss function for our problem. The other parts are the same. We use RMS prop and the accuracy as our matrix. So what's the difference between ReLU and the sigmoid function? ReLU is called the rectified linear unit function. Actually, it's just ignore all the input less than 0. So whenever you get the input x less or equal to 0, you make the output 0. Otherwise, you just pass the input as output if the input is larger than 0. So it's called the rectified or linear unit function. It's a linear function if the input is larger than 0, otherwise it outputs 0. For sigmoid function, it's the output between 0 and 1. Here's the formula of sigmoid function. We love sigmoid function because it has good property of derivative. So you can view this as a probability between class 0 and class 1. The more closer to one side of class, or to, for example, to class 1, then the higher probability the review is positive, in our case. One thing to note is that, as we mentioned before, classification is actually a discrete problem, right? But the output of sigmoid activation function is continuous. So we need to make a threshold, right? We need to find the decision boundary. We need to decide the decision boundary. And the boundary can be changed. So we can use the RC curve to evaluate the performance of our detector. You may be curious about that, why we need activation functions. Why are they so important? So here are some explanations. Without an activation function, the dense stairs just consist of two linear operations, dot product and addition. So multiple layers are just multiple linear transforms, and eventually a large linear transform. This hypothesis space is too restrict, and won't benefit from multiple layers of representation. So we need activation functions. The other evidence is that our neuron in our brain is also works like with an activation function. Our neuron is only activated when the accumulated chemical or electrical instance exceeds some threshold. So this is how our brain works. Our neuron has biological activation functions. Now we can compare our model. In addition to just pass the name of the loss function and the optimization algorithm or matrix, you can actually have more choice. For example, you can import optimizer from Keras, then pass the learning rate. So you can adjust the learning rate. Actually, Keras gives you more freedom. You can define your own custom loss and matrix. It's possible. So you can also import other loss library and the matrix library, then call the corresponding loss function and the matrix. You can use, for example, binary accuracy. So Keras is not just simple, but also very flexible. Now I want to introduce an important machine learning trick that can prevent overfitting. It's called validation set. The idea is simple. We just use a separate data or split the data from the training data and pretend them as test data. We can use the validation set to monitor the model's accuracy during training. So we will see how soon. So let's first select the first 10,000 data as validation set. In practice, you can use cross validation or split the test training data into different sets and use each set as validation data in turn. Here we just randomly select the first 10,000 data from the training data set. Let's start train our model by pasting the partial training data and the validation data. So we select the first 10,000 samples as our validation data, and the rest are the training data. We pretend that the validation data are test data. And then we select the batch size. We use a larger batch size here, which is 512, and then 20 epochs. Okay. We'll go through all the data in the training data set 20 times. The most important thing is that we now save all the progress in the history object, and then we can plot the history to see if our model has overfit or not. After training process is finished, we can plot the results. Here's the loss function. We can plot the change of loss during each epochs. So you can see a downward trend of the training loss, or the dots are training loss. It keep go downward, alright. So why not we select a very huge epochs? So we will get a better results with more epochs. It's not how machine learning works. And let's look at the validation loss. It tells us different stories. The validation loss start to go up, right, after around 2 epochs. Right. So this means overfitting. Our model has better accuracy on the training model. However, it has worse loss on the validation set. So it means the model start to overfit on the training data. This is why the validation set can be used to monitor and prevent overfitting. Whenever there's a crossover, or let the validation loss start to rise, then there's a possible overfitting. To plot the result, we need to use the history object. We get the loss value of each epoch from the history dictionary, and then get the validation loss. We use the matplotlib to plot this figure. This is a very helpful trick. You can also use accuracy to observe overfitting. It's almost the same as loss function, just with reverse trend. So you can see that the training accuracy keeps going up, while the validation accuracy doesn't change and going lower slightly. So you can see the crossover happened at a similar place around 2 epochs. So we don't need to use 20 epochs for training our models after we have plotted the loss and accuracy history. After seeing those figures, we know that more epochs lead to overfitting. Finally, we need to evaluate our model on test dataset. The accuracy is around 84.42%, which is very close to our validation set accuracy, right? So this shows you how the validation set can help you to prevent overfitting. The validation accuracy is more close to the accuracy you will get on test dataset. Now we can use our model to classify the movie review. But remember that we use the Sigmoid function as our final activation function, and the output is continuous. So if you apply the predict function to the test dataset, it returns the probability. It returns the output of the sigmoid function. You can view the output as the probability of being positive. So the higher the number, the more possible the review is positive. If you want the binary classification, you need to define the decision boundary. It's a trade-off between recall and the precision. Of course, you can simply set the boundary to 0.5. Otherwise, depends on your application. You need to find a trade-off. You can plot the PR curve, precision recall curve, to observe the performance and find the decision boundary. The second example is to classify the financial news of Thomas Reuters. So we want to classify the financial news. There are 46 topics. This is a multi-class classification, which is the same type of problem as the MNIST problem. The Reuters financial news is a subset of the Reuters 21579 dataset from the UCI machine learning dataset. UCI machine learning has many open source datasets that we can use. It's a single label multi-class classification problem. In our subset, we have 8,982 training samples and 2,246 testing samples. First, we load the data from Keras. Now we import the Reuters dataset. And again, we just want the top 10,000 most frequently used words. So we set the non-words to 10,000. It will load the train data and the test data, as well as the train labels and test labels. The financial news are also encoded as a series of integers. So we can use the same method in previous example, in the movie review example, to decode the word ID list back into English. So first we download the word index dictionary, then we build a reverse word index dictionary, and then we look up all the integer, all the ID in our training data. Now we choose the first news. So we convert all the ID in the first news and join it as the decoded news wire, and we print the news wire. So here is the example. The question mark represents the word that we didn't use. So question said, as a result of its December acquisition of Space Corporation, it expects earnings per share in 1987 of 1.15 to 1.30. So it's a very old news, right? It's 1987, but it's financial news. Then we need to convert the word ID list into the one-hot encoding. Right. We can use the vectorized sequence function that first introduced in the movie review example. So we build a large zero matrix first. Use the number of rows equals to the number of articles, and the number of columns equals the number of the most frequently used word. So the number of rows are total training samples, right? Total samples in the data set, and the dimension, the number of rows is 10,000. So whenever we find a word ID, then we set the corresponding entry to 1. So this is how we vectorize the sequence. We have done the same thing in the movie review example. So we convert the train data and test data into the X-train and X-test data. And also we convert the train labels and the test labels into one hot train labels and one hot test labels. This is the same as MNIST dataset. We call the two categorical function to convert our label ID into one hot encoded vector. We also want to use the validation trick. So we select the first 10,000 samples as validation set. Okay, so here we use the first one to the 10,000. We split from the first one to the 10,000 the data as the validation set, and the rest of the data you can omit the second index to mean to the end of the array. The rest of data are used as the partial as a training data. It's called partial train. And repeat this process for the labels. Now we can build our own neural network model. Again, we choose to build a 3-layer network. The input is 10,000 dimension, but output is 64 because we have 64 topics. We have 64 class. So the output size is larger than movie review. We select a hidden layer with larger number of neurons. We set it to 64. So we have two 64 neuron hidden layers here. Okay. And for the multi-class classification, we choose categorical cross entropy as our loss function. For the matrix, we also use accuracy. And the optimizer is RMSprop. We train our model by passing the partial train and the validation set to the model. And we select 20 epochs and the batch size 512. Here's the results. So the initial accuracy is around 0.64 and gradually increased to 0.8, which is not bad for 46 class dataset. Let's plot the training accuracy versus the validation accuracy. As we can see, the validation accuracy starts to saturate around 6 epochs, and the validation accuracy is around 90%. Okay, so we don't need too many epochs. Maybe 7 or 8 is enough for this data set. The performance on the test data set is around 64.93, so it's close to the previous 80% on training data set. It's slightly lower, which is normal. Okay. So here's the result. We call the evaluation function and pass the test set and the one-hot test tables to the evaluation function, then print the results. In addition to the one-hot encoding and the cross entropy, we have different ways to handle the labels and the loads for multi-class classification. In fact, we can use integer labels, or just use the integer as our label, and we don't need to convert it as one-hot encode. And if you use the integer label, you need to choose the sparse categorical cross entropy. However, in practice, we choose the one-hot encoding most of the time. Here is a brief summary of multi-class classification. First, to classify n classes, you need to set output layer size to n. And in a single label multi-class classification problem, the output layer should choose softmax with n output class. And the categorical cross entropy is the go-to loss function for the classification problems. Of course, you can choose integer labels, but it's seldom used. So there's two ways to handle labels. One is one-hot encoding plus categorical cross entropy. Another one, which is seldom used, is labels encoding as integers plus the sparse categorical cross entropy. The third example is to predict the house price in Boston. This is a regression example because house prices are continuous data. We'll use the Boston housing price dataset. The goal is to train a model to predict the median price of homes. This is a small dataset with only 506 samples, and each sample has 13 features. Here is a table of the features. The first is the crime rate, per capita crime rate by town, and the second is the proportion of residential land zoned for lots, and the proportional of non-retail business area, or whether the house is close to Charles River or not, and even the nitrogen oxides concentration, or the average number of rooms, or the age of the house, and the distance to employment centers, and the index of accessible radial highways, or tax, or even pupil-teacher ratio. So maybe teacher is important for the housing price. Okay. The first step is to load the dataset from Keras. So we can import the Boston housing dataset from the keras.datasets library and call the load data function to get the train test split. The next step is to normalize the data. In this case, we want to make all the features center around 0 and has a unit standard deviation. Note that we can only use the training dataset to calculate the mean and the standard deviation. We can never use the information of test data. So we first calculate the mean and the standard deviation of all the samples, which means we calculate the mean along the first axis, then subtract the mean from all the data. For the standard deviation, we also calculate the standard deviation of all the samples, then divide all the data by the standard deviation. Then we normalize the test data using the mean and the standard deviation of our training data set. After normalization, we are ready to build a model for predicting housing price. The biggest difference from the previous models is that our network does not have an activation function for the final output layer. So we just end with a single unit. Here is the final output dense layer. We only have single output, the housing price, and we don't have activation function. Then we choose the mean squared error as our loss function and the mean absolute error as our matrix. Another difference is that we define a function so we can reuse reuse this function and build the model several times. It will be useful for the data cross validation. Okay, so in this function we create a sequential model and end two hidden layers with 64 neurons, one output layer with single unit, and then compile and return the model. In previous examples, we just split the first several thousand data as the validation set. However, there's no guarantee that the first thousands of data can represent the whole training or test data set. So another trick is to do cross validation. cross-validation can lower the variance of validation set. So, for example, we can split our training data into 3 subsets and select one subset as validation set and use the other 2 as training data set. This is called the threefold validation. Then we use 1/4 of the subset one by one and train our model 3 times. So we will have 3 scores. The final score is the average of the 3 training results. In practice, we can split data into any number of partitions. So this trick is also called k-fold validation, k-fold cross validation, where k is the number of partitions. Now let's implement the k-fold validation. Okay. We first need to define the number of k, and then we calculate the number of validation samples for each split. Okay. Then for each split, we first separate the validation data from training data using the index of the split ith split. So the number of validation samples from I multiplied by number of validation samples to I plus 1 multiplied by number of validation samples. So we also split the training labels, and then we concatenate the split of data before the validation set and the rest of the data. So we use the other split as our training data. So and then concatenate the data. This is our partial training data. Then we do the same thing for the training labels. After that, we need to build the model. So that's why we define a function that can reuse the code of building models. So for each validation training, we need to build a model. Okay, then we can use the partial training data to fit the model, and then we evaluate the results on the validation set. Finally, we save the results of for each split so we can visualize the final results. In this case, we do a 4-fold validation. Well, the number of k is 4, so we do the training 4 times. After the k-fold cross validation, let's visualize the average mean absolute error scores. So first we calculate the average of our MAB history. Then we use the matplotlib to visualize our results. We can see that the error decrease rapidly at the first several iterations, for several epochs. In this example, we have done 500 epochs. This is because our data set is small, so we can do each epoch rapidly. So we can see from this figure that the first several data points are on a different scale than the other points of the curve. So to better visualize the result, we can do a smoothing. We can smooth the MAE score just by remove the first 10 data points. So all the data points lies in a same scale. In addition, we can replace each point with an exponential moving average. We can use a moving average to smooth the curve. So this will help us to better understand our results. Here is the smooth curve function. We pass all the points to this function, and we define a smooth points array. And for each new data point, we get the last point from the smooth points, then calculate using a weight average, or then append a new point into the smoothed points. So then we can use the smoothed curve and visualize it. Finally, after we know which epoch is the best for our model, we can train a final production model using all the training data. Because the validation set is just part of our training data, so we can use it. So after we find the best parameters, don't forget to use all the training data to train the final model. Usually, the more the data, the better the model performance. Okay, let's evaluate the final model on the test data set. Okay, so the result is the mean absolute error of 2.7883. So what's the metric is $10,000. Is it a good result or not? Let's see the average of the test target. So the average is around 23. We have a less than 10% error. Also, we can visualize our model. Our model only have 5,121 parameters because we only have 13 features and 2 hidden layers with 64 neurons. Here is a summary of what we have learned in the housing price prediction example. First, the final output layer of a regression model has no activation function, so we only need one single unit to output a value. And second, we can use the mean square error as loss function and the mean absolute error as the metric for the regression problem. And for all the problem, data need to be normalized. Also, we can use k-fold validation to prevent overfitting and reliably evaluate the model. And remember to use a small network for small training data to prevent overfitting. Here are the key takeaways of today's class. First, we can import model set layers from Keras, then use models to create a sequential neural network. Then we can use add function to add as many layers as possible and compile it and assign the loss function and the metric. Use fit to train our model and use evaluation to test on the test data set. In deep learning, solving different types of problems means just select different active function for the next layer and use a different loss function. So this table is the most important information of today's class. Please remember to choose the right activation and loss function for your problem.